So in this particular video, what I want to do is to talk to you about the different network types that we can have with our OSPF. Now you may recall from the previous skill, we had this concept of a DR, let me try to write that correctly, again, a DR and a BDR. Remember, this was a designated router and a backup designated router. Now these concepts ultimately came into effect when we were dealing with a broadcast-based network. Pretty much what we're seeing here is that when we have an Ethernet link, then it is a broadcast network, at least by default, and thus this election of the DR and BDR is going to take place. So you might remember with respect to the election, the router with the highest router ID would be elected the DR, and then the one with the second highest ID would be elected the BDR, unless you happen to override that behavior and specify a higher priority level on a particular interface. So remember, the default priority is 1. If you happen to specify a particular interface to have a default of, let's say, 2 or 3 or 4, whatever it may be, that is going to influence the decision, and that will ultimately help us decide who the designated router is going to be. So you can imagine all of this going on is going to take up some CPU utilization on the actual devices themselves participating in this election, and more crucially, it just takes a bit of time. Now the additional time this takes up is more time that the network is not in a converged state. And quite simply, the quicker we can converge your network, i.e. the quicker everyone agrees all the roles and we can begin exchanging routes and passing traffic in a reliable manner, the better that is for our network performance. So really, if we can ultimately pull down this time, or better yet, completely eliminate this additional time, this is a good thing to consider. Right, so look at this topology right here. Let's just temporarily ignore these links, okay? Let's say these interconnects between the switches do not exist, okay? And instead, connecting all of these devices is a regular layer 2 switch, okay? So one right in the middle here. So what that would mean is that each interface, i.e. this interface here, this one here, this one, and this one, they would all be put on the same subnet. So you can imagine if we were using an IP address of, I don't know, let's just go with 172.168.1.0/24, okay? This interface here could be 172.168.1.1, this could be 1.2, this could be 1.3, and over here could be 1.4. And here is the thing, because we truly have this shared segment, the ability to broadcast is very, very important, because if this device is going to communicate, it's not necessarily just going to always communicate with, say for example, this one right here. It might also want to talk to this one, or it might want to talk to that one. Basically, it has more than one option about who it's going to be talking to. So again, in this scenario, it is going to be a broadcast network, and thus the election of a DR, such as, let's maybe go with, imagine this is a DR, and this one here can be the BDR. This actually makes sense in this type of topology, because then we could have these other two devices just configured to be DR others, and they would only have to form a full adjacency with this one here and that one there, as opposed to a full mesh between absolutely everyone. And this just is highlighted even more if we had an even bigger Ethernet segment, as opposed to having 4 on a shared network. Maybe we happen to have 20 or 25. Okay, so obviously the DR BDR is a good thing, but look at the topology we have right now. In the case of this shared segment right here, because this is an Ethernet link, then by default we are still going to have this election of the DR and the BDR. But that of course still takes a little bit of additional time and compute. Same thing as here, we're going to have an election here, as well as here, as well as here. So effectively in this topology we're going to have 4 separate elections. But look at this right here, when we want to talk over this link, the only end speaker is this particular link right here. So if we want to talk out of this interface, it doesn't really make sense to broadcast anything because it's always going to go to this one. And similarly, if we're talking OSPF out of this interface, it's always going to go to this guy right here. 1-to-1 communication, or rather point to point. Now way back in the olden days, a really common connection was a serial based connection. Now these serial connections happen to be much slower than modern Ethernet connections. So quite honestly, you're not going to see them quite as much as you would have back in the day. But here is the thing, these serial connections were effectively going to be using the point-to-point protocol. Basically, this was not going to act like a broadcast link. It really was one side of the connection talks to the other side, and that is it. Now here's the thing, despite the fact that in OSPF we are using these physical Ethernet cables right here, we can still make them act like a point-to-point connection in respect to OSPF. Now ultimately what we're doing here is we're going to this link and saying, hey, by the way, don't even have an election. You only have one peer as a point-to-point connection, just save the time, transition to the full state as quick as you can. And again, we can repeat the same thing here and here and here. So as opposed to having these 4 elections determining the DR and the BDR, instead we can just say, hey, we want 0 elections based on the physical topology that we're running with. 1-to-1 communication here, 1-to-1 here, 1-to-1 here, and 1-to-1 there. So let's go and configure OSPF on our devices, and we'll make the modifications and see how things shake out. Alright, so let's just go into our devices and configure OSPF. So switch 4, let's just start with this one first. So configure terminal. We'll say router OSPF, give it a process ID of 1. I'll configure the router ID to be all the 4s. And I will go in to each interface, so interface 111. And I'll say IP OSPF, process ID 1, put this into area 0. So I'm going to have to create this area, hit Y and enter again. Exit back out, go into interface 112, follow the same process, exit out, interface 113, OSPF 1, area 0. Okay, let's go to the next switch. Okay, so we have switch number 3 here, same process, router OSPF 1, give this the router ID of all the 3s, go into interface 111, IP OSPF process ID 1, area 0, create the area 0, go into interface 112, activate OSPF, same on 113, activate OSPF. So let's go on to switch number 2, same process, router OSPF 1, router ID can be all the 2s in this one. Interface 111, IP OSPF 1, area 0, create the area itself, and do the same for interface number 2, as so, as well as interface 3. And then lastly, we go on to switch number 1, configure terminal, say router OSPF 1, router ID of all the 1s, go into interface 111, IP OSPF 1, area 0, create the area, and repeat for interface 2, as well as interface 3. Okay, so with that done, our adjacencies should begin to form. Okay, so if we go to switch number 1 to show IP OSPF neighbors, as we can see here, we do indeed have a full adjacency established with both of our peers, which is switch 2 and switch 3. And remember, very crucially, switch 2 is the DR, it has the higher router ID, and switch 3 also being a higher router ID, it also is the designated router. Go to switch 4, show IP OSPF neighbors. We can see we have an adjacency with switch 3 and switch 2, and they happen to be the BDR in this transaction because they have the lower router ID and we haven't modified the priorities. So here's what we're going to do. We're going to go into these interfaces and we're going to actually change them so that they are not actually a broadcast-based network. This is going to effectively terminate the election, and thus we'll have a different output on our screen. So if we go on to switch number 4, let's just look at the topology here. We want to go on to interface 113 and 112. These are the ones that are actually connecting to the switches, such as here and here. So interface 113. So we'll take the command IP OSPF network to specify the network type. And if we look at the options, we can specify a broadcast network, which is the default, or a point-to-point network. Let's change it to point-to-point. So if we go and do the same thing over on switch 2 to match the other side, so that's going to be interface 113 on switch 2. So interface 113, IP OSPF, network, point to point. So now if I exit back out and I do a show IP OSPF neighbors and to enter, notice the difference in the output here. The priority value is not applicable anymore. We're not actually caring about an interface priority for an election. And more crucially, the state of the connection we have with switch number 4 is simply in the full state. We don't see a DR or a BDR or anything like that, because now we are no longer running an election over that particular interface. And the same thing will be true over on switch number 4 if we just check the conditions, or rather the configurations. Show IP OSPF, neighbors, and to enter, we'll see the actual connection we have with switch number 2. The interface priority no longer applies, and we only have a full state, no longer a connection with a DR or a BDR. So effectively, because we have that direct connection over this particular interface to only one device, we have essentially simplified and streamlined our OSPF connections. And by the way, if we so wished, we could easily repeat that process over this interface, as well as this one, as well as this one here.